It's a pleasure for me to start the lecture program of CIDR. I ran into a little bit of a cold, or a cold ran into me, I guess is the physical term, so I hope I'll get through this without croaking too much. But one way that I discovered that if you have a cold in your lecture, that the role really needs to switch from lecturing to audience participation, and so I'll try to engage you as much as possible, at least in the beginning, for that. What I'm going to do is to provide you with a very broad overview of how we use geophysics to study subduction zones. This, of course, is an impossible topic because there's an enormous amount of geophysics and enormous amounts of subduction zones, and so all I'm going to do is to really provide a few highlights of how we study things and talk a little bit about how we understand the usage of geophysics. This is primarily intended for the non-geophysicist in the room, or the seismology for the non-seismologist, and the geodynamics for the non-geodynamicist, etc. I think that is the best approach to CIDR that I've seen work. So if you get a little bored when I explain receiver functions, it's okay. You won't be bored when Christy talks about the geochemistry of subduction zone this afternoon. So a quick overview. I'm actually going to start with mantle convection and try to demonstrate to you that a long time ago we already knew a lot about what we now know as plate tectonics, even though it was not named plate tectonics at the time. And I'm going to give some geophysical applications of studies of how we look at the incoming plate, what's happening as the plate is subducting, the deep processes, where deep in my terminology here is relatively shallow for the deep earth scientist, and then we'll move back up through the mantle wedge and the overriding plate. A lot of this work has been, a lot of work that I present is based on work that's sponsored by both Margins and Geoprisms, which is our 2 decadal programs to study subduction zones and continental margins, including rifted margins, from a terrestrial and oceanographic perspective. And so this is one of the few programs that get support from both OCE and EAR in the National Science Foundation. So to start off, is it possible to reduce the light a little bit? Or, okay, so in order to start, and I really would like you to feel very comfortable asking questions, and maybe in particular the students and the postdocs before the senior participants. So feel free to interrupt me anytime when something's not clear or you have a question. And to start off this process, I just want to get to a few questions from you. I mean, what mountain are we looking at here? This should be straightforward. This is Mount St. Helens, lateral blast. 37 years and a month ago, it exploded sideways, killing a few people who were in the wrong side of the volcano. We had a meeting in 2009 where we took a field trip with a number of the international participants, and we all took pictures of this hazy mountain, and Ikukovada was the only one that was smart enough to put a few of these tree stumps in front of it, making for a much nicer framed picture. Okay, second one, Adam cannot guess, and Sarah cannot guess either. This one might be a little harder. Which mountains are we looking at here? This mountain looks a little bit like Mount Crumpet from the Grinch. Any guesses? It's also in the Cascades? No, it's not. Can you speak up, because It is Jefferson, yes. This is Mount Jefferson, and behind it, very vaguely, you can see the Three Sisters. This picture was taken during the 2009 meeting that we had on Mount Hood. They have a very nice timberline lodge there, and this was the view we had at breakfast. So fantastic, so everybody was taking pictures. And then as the meeting started, this enormous PowerPoint screen came down, and the room got dark, and we might as well have been at Denver Airport, or UC Berkeley for that matter. Those are Rocky Mountain ravens. There's actually a second one that's hiding right there. They love the garbage that's being put out by the folks at the Timberline Lodge. So let's start with some history, and I'm going to show some old people, and I would like to ask you, well, at least it keeps us entertained, right? I'd like to ask you if you know who this person is. This is a German scientist. He's a meteorologist and a polar explorer. Wegener, Alfred Wegener. He was a heavy smoker, He didn't live very long. In the 1930s, he died on Greenland as part of an expedition. Everything went wrong there. They had frostbite. He skied himself to death. He got a heart attack and was buried in Greenland. But of course, he was very important in providing the theory of continental drift, which now in retrospect was something that we all feel very comfortable with. The idea that we had Pangea, which is found by overlap in geological terrains, in overlap between fossil species that diverged as soon as the breakup occurred. And importantly, from Wegener's perspective, glacial features, including glacial striations, that strongly suggested that a number of these continents were on the South Pole, whereas aside from Antarctica, most of them are not. Unfortunately, this ran into a little bit of trouble. Particularly the seismologists were not the friend of continental drift. Seismologists had a good argument, I will admit. They said, well, S-waves penetrate through the Earth's mantle, therefore it's a solid, therefore it cannot move. And unless you had entertained yourself about Maxwell time and the idea that rocks can flow over long time scales, this was a strong argument. And Wegener was pretty philosophical. A year before he died, he wrote kind of the idea, in a way I like it, I also find it very tragic. The final resolution can only come from geophysics because it's the only science that is precise enough. Were geophysics come to the conclusion that I was wrong, I will gracefully admit defeat. So the geophysicists were the problem makers, and he thought that they were the solution. In a way, some of the geophysicists provided support for his idea. So here's this gentleman, two pictures, one just before he died in the 1960s, University of Edinburgh. He's a British fellow of the Royal Society. He was a geochronologist. He was interested in radioactive decay. And he supported Wegener's idea that continental drift was supported by mantle convection. His first name is Arthur, and his second name is Holmes. Okay, Arthur Holmes. He provided the idea, since he was interested in radioactive decay, and he was one of the first early people who tried to make estimates of the age of metamorphic terrains. He estimated some terrains to be 1,600 million years, which at that time was much longer than what people really like to think about as the age of the Earth. But he also knew that radioactive decay could create heat, and that could therefore fuel mantle convection. And so his idea from the 1930s is really not that much different of what we see in textbooks. This is just an idea, there's no direct support for it, but the support was provided in large part by this gentleman, was an early marine scientist. He measured gravity by a very long distance. He is my academic grandfather. You know his name, Ingrid? You were at Utrecht, his famous date in the 65. He was a very tall man, a little taller than I am. You can see him up here standing amidst people that were on the underzeeboot or the submarine. I don't know whether he was wearing that tropical helmet because he was in Indonesia or that he needed something to protect his head as he was aboard that very small submarine. But what he did was to develop gravity measurements and use the submarine to get below the waves, and was therefore able to do the first marine gravity measurements. Anybody? Yeah, Waning-Meines, excellent. Felix Waning-Meines. He's one of the people that actually... Oh, I forgot to mention, Arthur Holmes also died on his skis. He had a heart attack while recreational skiing, so Waning-Meines died in his sleep, I think, in 1966. His major contribution was the development of new gravimeters, and very spectacularly, and if you have never seen this, this is worth looking up, gravity maps over the Indonesian, what we now call the Indonesian Trench or the Indonesian Arc, with very large negative gravity anomalies, with slight positive anomalies outward. And this is what we now would recognize as just the trench and the Fore-arc bulge. At that time, we didn't have good observations of the seafloor. It was too deep for most submarines, and the gravity provided that first idea. So what this led to was the idea that we have missing mass, and that's really weird, because if you're missing mass, of course, the stuff will fall in and will fill that in. So if you have this missing mass, it must be dynamically supported. And this really was the first confirmation of the Holmes convection idea to support continental drift. This is all in the 1930s. an American who kind of tied everything together. There's a high-pressure apparatus named after him still. He was the first person to deform, or not the first, but one of the first people to successfully deform rocks and demonstrate that mantle silicates actually deform as a fluid over geologic timescales. His first name is David, and the second name is, you can't participate. The second, well, yeah, of course you can. Second name is Griggs. He wrote a very nice article that's still incredibly readable in 1939. And his major contribution was to add this idea of fluid dynamics to mantle convection, strongly supporting the Wegener support for, or the Veening-Meijner support for the Holmsen idea for Wegener. And in 1939, this is easily accessible, Theory of Mountain Building from the American Journal of Science. Everything ties together. There's some even convection models in there from Peckeris that essentially do the same thing as what us mantle dynamicists do now. 1939. And we didn't know mid-oceanic ridges at that time, but we knew about essential subduction. A very important contribution, Griggs doesn't name him in the article, but a very important contribution was made in Japan by Mr. Wadachi. That's how you pronounce the TI. And what he did was to have very good evidence for deep source earthquakes going down to 600 kilometers or thereabouts below Japan. And here is a map from him from 1935, showing below Japan very deep earthquakes, in this case going down to 300, 400, 450, with a relatively flat geometry below northern Japan, steeper below the Kanto region down to Izubenin. In Ryukyu, relatively steep, no deep earthquakes below Nankai. If you look at this, you could have made this as a slab surface map today. Maybe it's a little bit more precise these days, but the essential information about subduction zones and earthquakes in there was known in the mid-30s. So by 1939, everything was ready. Unfortunately, the seismologists had a really strong voice in this, and they contained the idea of continental drift to be a silly hypothesis. Here's somebody who grew up in Michigan. She got a master's at the University of Michigan, then moved on to Columbia University. She died about 10 years ago. Marie Tharp. She was able to get access to US Marine ship tracks and submarine tracks that she couldn't publish because it was protected data, but she was allowed to make interpretational maps of that, and you've all seen these particular maps either on the walls of your institution or in textbooks. In 1957, she was the first to look at a detailed map of the North Atlantic, very strongly highlighting the mid-oceanic ridges as the complement to the subduction zones, even though at that time it was not known that there was actually rifting at that. Here's another person who had an untimely death. He got murdered in 1995, the week before AGU. It's a robbery gone wrong. He's a paleomagnetist, an Englishman. This is Keith Runcorn. He was the first to use paleomagnetic methods conclusively and convincingly to demonstrate that if you wait on a continent, you see the pole drift, or the continent is drifting with respect to the pole. And so he was able to illustrate by taking polar wanderpath from North America and polar wanderpath from Eurasia that the pole drifts in different directions. And the best way to make this match up, if you have only one magnetic pole, is to make the continents drift. And so this was the first fundamental proof from geophysics that continental drift was actually working on the same geological timescales that Wegener suggested, although Wegener was off in a lot by his geochronology because there weren't good radiometric dates at the time. I think people started slowly accepting in the 60s. Some people argue that 66, 67 is kind of the birth of plate tectonics, so roughly 50 years ago. But a fundamental paper by Vincent Matthews from Cambridge was where they towed a magnetic instrument across the Reykjanes Ridge and saw the beautiful symmetrical banding that clearly indicates that as the Earth's magnetic field, you record different magnetic signals and as it's spreading. There's actually a paper from 1962 from a Scripps scientist that showed the same thing, but then for Juan de Fuca. So it might be interesting to go back in time to actually figure out who was the first to figure out that mid-oceanic ridges were drifting. But that was when we got to plate tectonics. So you see that just by having people have a wrong argument about the Earth dynamics from seismology holds or held back progress into essentially plate tectonics and mantle convection for about 4 decades. So hopefully we can be better and talk to each other about the limitations of our science and our understanding that we don't know everything from one discipline. So that's what CIDR is good at. So it's a little bit of a dark picture with this light, but what I've highlighted here are already a number of processes where geophysicists study essentially subduction zones in plate tectonics. We looked at the earthquake distribution from Waddaci. We looked at geodetic studies from Penny-Meines, interpreting the dynamics of subduction zones. These days, of course, we also use the GEO, GPS, and INSAR. They provide very clear indications about how slabs are subducting and deforming at depth. Paleomagnetism looked at continental drift. Of course, many paleogeographic reconstructions as well, demonstrating this much more precisely than what Runcorn did. We can also look at the structure of subduction zones from magnetic methods. Deformation studies, this is Griggs. Of course, deformation studies kind of starts blending into petrology and therefore geology and geochemistry as well, so it's not strictly a geophysical study per se. Heat flow measurements as a separate component about seeing what heat comes out of the Earth. And one thing I will not address in this talk at all is modeling. Modeling has multiple forms. It can be done by just taking forward models using conservation equations of mass, heat, and energy, and understanding some constitutive equation, and then you can model a subduction zone. But you can also use modeling to much improve data interpretation, data inversions for tomographic techniques, for example, understanding where things happen. And so modeling is a very broad application, and I'll not really address that in this talk. My technique is failing me. I've been a professor, or not been a professor for too long. I always thought of an intro geology. It was always a good idea to just stand still for a little bit and I'd take a sip of water, and somebody would raise their hand and say, "Hey, can you?" Pause. Thank you, Doug.
So you left out the fact that a seismologist was the first one to propose that subduction zones actually go down and show that they're continuous with the plate on the Earth's surface, which was Jack Oliver based on attenuation studies in 1967.
Well, I guess you have to improve on me in your upcoming talk on that one.
So although seismologists led people astray for a long time, we eventually
The seismologists, I will agree with Doug on this one. The seismologists did redeem themselves once the shells fell off their eyelids. So subduction zone, for anybody who doesn't know the ETH color scale that Taras Geria has imparted on us, this is the ETH color scale. Beautiful purples and oranges and primary colors and everything in between. It's if there's purple, it comes from Taras Geria's group. This is one of many cross sections through a subduction zone you can draw with some indication of processes. This is not a complete diagram, this is not a correct diagram, but it indicates some of the processes that are going on. We have an incoming plate. We know that there's actually a lot of very interesting dynamics going on in the Fore-arc bulge, where we have faults dipping down. We know that slowly as the slab is going down, it starts locking. We get a seismogenic zone, at least on seismic timescales it's locking. We have big underthrusting events. This tends to end near the moho in most subduction zones. And there's this very intriguing separate part of deformation that occurs on different timescales than typical earthquakes, which can be caught in the general term episodic tremor or slip, or ETs, which occur, well, up dip and down dip of the seismogenic zone, and maybe even deeper. We have good evidence that in some subduction zones, the region that is below the Fore-arc, so before the arc, that this region is a little bit special. I'll show some geophysical evidence for this. It may be that there's a lot of serpentinite in there, but certainly this part doesn't seem to participate very much in the convective flow as the slab is being dragged down and hot material comes in. And then we somehow create dehydration, we somehow create stuff going up that eventually gets up in the arc. And that's a big question still about how exactly this happens. We have intermediate depth earthquakes, which are of great interest because they occur on depth that normal brittle faulting doesn't work anymore. The confining pressure is too high. So we need to find ways to make earthquakes under high pressure by local weakening of the rock at those depths. So I'll use just some examples, and if I run out of time, I run out of time. But I'll try to start on the incoming plate, look a little bit at the seismogenic zone. I'm going to ignore the Fore-arc in detail itself, look at some deep slab processes, down from 80 kilometers to a few hundred kilometers, and then bring us back up to the volcanic arc. I will have borrowed, and I've indicated the slides that I borrowed from a subduction zone meeting that Geoprisms organized 2 years ago at Redondo Beach. Some of you were at that meeting, and we had a great student symposium ahead of that, which allowed us to kind of discuss at an introductory level the type of processes that are going on both in geochemistry and geophysics, and I've borrowed some of those slides. So the incoming plate, this is of course Geology 101, but it might have been a while since you took Geology 101. The incoming plate has a basaltic crust of roughly 7 kilometers on top of a archbagitic or slightly depleted peridotitic mantle. At the magma chamber, dikes are feeding magma into the extrusive of the pillow basalts. This extrusive section of the dikes plus the pillows is roughly 2 kilometers. And then the magma chamber solidifies and causes intrusive rock, or the gabbros. It's a rather boring crystalline rock. At least I think it's boring, although I have it in my kitchen. They sold it to us as granite. And it's just a gabbro. Yeah. Gets a lot prettier on the Mantle side. Beautiful picture from Cinti Lee of peridotite nodules included in mafic material, where these came up from 30 kilometers, demonstrating what the mantle looks like. Even at the ridge, this crustal pile is affected a lot by hydrothermal circulation. We've seen for the last 35 years or so big evidence of black smokers, which indicates hot material or hot water coming up from deeper down. And we think that the hydrothermal circulation is principally limited to the extrusive part of the pile, with the gabbros not necessarily participating as much. It's a little hard for us to tell what's happening in the gabbros, as there's been only 2 drill holes that I know of that have gone into the gabbro. And so we have, aside from exhumed terrains or ophiolites, we have little evidence of what the gabbros in the Mantle section directly looks at that. So geophysics helps us to identify what's going on.
Hey Peter, can I just point out, I can couch this as a question, but the sort of the ball and stick magma chamber, or what's affectionately called a ball and stick magma chamber on that top cartoon is very widely viewed with skepticism now. So I understand this is just a cartoon, but I wanted to point out that if you look at Discovery Channel documentaries and things like that, they always have the ball and stick magma chamber with the witch's cauldron of bubbling magma, and it's probably doesn't really exist.
It is a Geology 101 textbook picture.
Understood. Yeah, they get also.
My apologies
like
for hurting your sensitivities at this early stage.
I just like that idea not to continue to be propagated.
Okay.
So I'm not giving you a hard time.
Well, let me move on then from this picture. Strike it from your memory. Where's the camera? Don't look at this at home. So really beautiful, you can barely see it, but it says crust here and Mantle, the moho or the mohovichic discontinuity separating the two. Beautiful seismic refraction study from about 15 years ago, Cesar Renero and others, providing some very intriguing ideas that as you get into the subduction zone, so the trench is right there, this is Nicaragua, overhanging plate is here, the arc is about or 500 meters over that direction, that you have very strong reflectors that look like down-dipping faults. And these faults, as you can see here, cross the moho and then soul out into the Mantle underneath it. Very intriguing idea that the crust and the Mantle below it are cracking as a consequence of the bending in the Fore-arc bulge. We now know that these provide actually efficient fluid pathways and therefore cause a mechanism to rehydrate both the lower crust as well as the Mantle. There's some good evidence for mantle hydration. Some early study by Ivan Ditch from roughly 10 years ago, where OBSs were put in this section with the normal faulting, and they saw a strong reduction of the seismic velocities below this bending, and this is the relative velocity difference with really marked velocity contrast. This could be done by the cracks themselves, this could perhaps be by anisotropy, but I think most of us assume that this is now active serpentinization, where the formation of serpentinite out of olivine causes lower seismic velocities. So if you think about what goes into a subduction zone, we don't have a dry crust, we don't have a dry mantle. Sediments are highly variable. Volcanic sheeted dikes maybe have about 2 weight percent. Gabbros is not known, but it's presumably less, some estimates of 0.7. And then for serpentinite, we don't really know how much goes down. In some regions, it's indicated that it could be a lot. In some places, there's no evidence for serpentinization. A recent study by Shillington et al. From Nature Geoscience a few years ago, where they put 2 seismic traces in the Aleutians. This is a region of interest, the Shumagan Gap here. You might be able, let me trace out the circles here. There's a circle, there's a big circle, or ellipse. Those are rupture areas of large underthrusting events in the Aleutians. And the Shumagans have not seen one of those large underthrusting events. And so that might mean that it will come, and it will be a big one, or for some weird reasons, this place is where there's no large seismicity in the underthrust. So they had a very nice active source seismic study. The bathymetry between the Shumagan Gap and the Samiti region, that's kind of a control over on the side here, already indicates massive differences. We get these very strong fault-bounded basins in the Shumagan Gap. We do not have them in Samiti. If you look at the seismic, it's a little hard to see, but where you have these faults, you can actually see these traces going down into the deeper part, very similar to what happened in Nicaragua. And from the seismic refraction studies, where essentially you measure the sound velocity going down into the crust, you again have in the Shumagan Gap relatively large amount of reduced seismic velocities, strongly suggesting serpentinization, whereas in the control section here, there are little variations, maybe suggesting no serpentinization whatsoever. So this is a great way for us to probe the petrology of a downgoing slab by using seismic methods. It's not just seismics we can use for this. There's a couple of nice papers by Sammer demonstrating that active source electromagnetic methods using ocean bottom magnetometers and a towed magnetic signal allow you to see penetration of high conductive anomalies. So this is resistivity, so the red is very low resistivity, the blue is very high resistivity, so this is low conductive channel, high conductive channels going down. Very similar, they also align with these regions where you expect a fault. So electromagnetism also indicate the potential for fluid pathways. Seawater is very conductive, and this likely is the direct signal of seawater penetrating into the Fore-arc bulge. An extension of that study into the trench demonstrates actually that fluids go down into the trench. Maybe they disappear here. Maybe this is where the active dehydration is happening, where the fluid phases are being squeezed out. And there's a very intriguing signal here that looks like it's fluids moving up that go to active seeps that are at the Fore-arc, suggesting direct fluid pathways of free fluids moving up and then being extruded in the Fore-arc region in Nicaragua. Is that about correct, Sammer? Always fun to present somebody else's work when they're in the audience. Second geophysical application goes into the seismogenic zone, and we have a number of really good specialists here, so I'm just going to touch on a couple of things, but it's not easy. There's a lot of diversity that we see in the behavior of the seismogenic zone, and a lot of diversity already comes in at the incoming plate, where sometimes we have these Horst and Graben structures, maybe water below it. We sometimes have seamounts that have a clear signal on what's happening in the Fore-arc, below the Fore-arc. And we know that there's a transition As the rocks get under higher pressure and temperature, there's a variety of dewatering, clay dehydration reactions that are going on. And at some point at a depth of roughly 15 kilometers is where we typically see the subduction zone lock with the overriding plate. That then, because it's slow deformation, it's moving in, and then the big underthrusting events release that stress over time. Where the seismogenic zone goes down to roughly 40 kilometers in most regions. So Billick and Lay, this is a very nice review paper looking at how the transition here happens and how it's influenced by heterogeneities along the slab surface itself. Something we've seen only in the last 15, 16 years now is a variety of deformation that is not on traditional seismic scales. Here's a nice example from Rogers and Dragert from Science in 2003, demonstrating that if you are sitting on the overriding plate, you move with the subduction, and then every year or so you kind of move back towards the trench. And this repeats over and over again. This is very nicely demonstrated by GPS stations, continuous GPS, demonstrating that you move. This is 1 centimeter, you move for about a year, and then you slip back. You move, you slip back, you move, you slip back. Very predictable, seen in Cascadia, seen in Nankai, is now seen in many other regions. Jeff, what is the record for, is it still 10 years now, the interscale?
Geodetically observed for now.
Yeah, okay. So some of these cycles go up to 10 years even, where we have this type of deformation that clearly releases stresses without large underthrusting events. And so this might be one of the reasons why Cascadia hasn't seen a very large underthrusting event since, what was it, November 1, 1700, as demonstrated by tidal gauge records in Japan. Associated with these slip events are large amounts of tremor that are seen along the subducting plate interface. And so this is generically called episodic tremor and slip. And we now know of very diverse variety of these processes at different frequencies, different length scales. It's beautifully complex. Some indications are that fluids might be related with this. Some indicates that we just look at deformation that's in between the traditional seismic brittle faulting and the more continuous mantle convection style ductile flow. From GPS we can measure where the plate is locked, where the seismogenic plate is locked. Here's some nice slides from provided by Jeff, mostly based on work by Mead and Lovelace. Where from GPS, the red regions here are the places where the seismogenic zone appears to be locked. That means that the blue regions are where they are not locked, and in some cases that's because of episodic tremor and slip that is seen in these regions. In some cases it's because of slow deformation after a large earthquake that happened before. But these places where you have this high coupling are of course of concern, because that's where you might see a large amount of, or the highest risk of big underthrusting events. And notice this paper is from 2010, and you can highlight this region. My apologies, I didn't explain that this was Japan on its side. Sorry, because of the big reds on top of it, looks a little weird, but here's Hokkaido, here's Tohoku. Tokyo is somewhere in here. There's Tokyo, and then Nankai and Kyushu over here. So that's a region where you expect big earthquakes to occur, and of particular this patch slipped in 2011 as the Tohoku Oki earthquake happened. And within 3 days, they had done their inversions and demonstrated that that locked patch that they had was really the region of the largest slip that occurred in the Tohoku Oki earthquake. So we can combine GPS and seismic observations to understand the seismogenic behavior at this shallow depth. We'll see more of this in the rest of the meeting. So moving down deeper along the plate, this is some work by graduate student of Jeff Abers, Doug Christensen. It's a very nice study across the eastern edge of the Alaska subduction zone. There's a road between Anchorage and Fairbanks where they were able to put seismometers down and provide the best detailed study of this region using seismic arrays, where they were able to highlight the local earthquakes and from that infer where the subducting slab is. There's other ways to infer the subducting slab in this region as well. I'm going to use this as an illustration of how we use other things than seismic velocities. Aside from seismic velocities, just reduction in P and S wave velocities, which might indicate serpentinization, for example, of where hot things are. We can use things like attenuation, or how non-elastic is the medium behaving, or we can use anisotropy and link that to active deformation. I'm not going to talk about anisotropy, but I just want to highlight how we can look at attenuation and understand that something special is going on in most subduction zones. This has been known for a long time from Japan, but it was a nice illustration from this paper, where from one earthquake that's being recorded essentially right above where the earthquake was, and one that was much further inland towards or much further towards the trench. This red curve, this is the seismic response that was seen at this particular station. This is the response that was seen at this station, where even if you're not a seismologist, you can just do pattern recognition, and you can see that if you look at the amplitude scale here, the amplitudes are much lower here. You also see that there are not that many high frequency signals in here. There's much higher frequency in here. The reason for the lower frequency content and the lower amplitude is that most of the seismic energy has been dissipated away by non-elastic processes like viscous deformation, grain boundary sliding, other type of things. This is quantified by the Q factor, or the quality factor, which is the inverse of the attenuation. The higher Q is, the more elastic, the more perfect elastic the medium is. And it's very nicely demonstrated that this high Q path is in, well, notice that this is about 100 kilometers depth, is in this region where the subducting slab is not that deep. Once you get below where the arc would be, you get these low Q regions. There were enough earthquakes and enough seismic instruments to do some seismic tomography on this attenuation. And so here's a nice diagram that shows a relatively high Q, high quality slab subducting with the earthquakes on top. Low Q wedge environment, which is kind of expected because that's where the fluids and the magmas are, that's where things are hot. You expect the medium to be not very conducive to perfect transmission of elastic waves. And then we have this corner here, which is a high Q corner that is very characteristic, and it goes down to about 75, 80 kilometers. We don't see this just in attenuation. We see this in seismic tomography of P wave and S wave velocities. We see this in heat flow. We see this in a variety of other places. Why this is here, we do not know. So if you guys can come up with a working group to explain this region, you would make me and Jeff and anybody else very happy, because we're banging our heads about this problem for a long time. This region has been, please, Doug, you got microphone? Microphone, please.
Peter, isn't it essentially a result of the fact that you have frictional sliding and slow slip events rather than viscous coupling across the shallow part of the subduction zone?
Well, the answer is probably yes, but we don't know why. So the mechanistic reason why at 80 kilometers something changes is not known. There's no known mineral phase boundary. There's no rheological change at those depths that makes sense why it's 80 kilometers. So Doug's question really goes into, in order to make this region, which is high Q, it suggests that it's actually taking away from the convective flow that happens in the Mantle wedge. So typically when we have a subducting slab, it couples with the overriding wedge. This is now coupling on geologic timescales, very important. It's not seismologic timescales. And so we get this inflow of hot material that is being brought down. And so continuously we make this Mantle wedge hot. We have this cold slab, we warm up the slab, fluids go in, creating the arc. That's our cartoon picture, and I think we're pretty much in agreement with it. But this region here is suggested to be excluded from that, because if the slab would couple here, the flow would go all the way up there, and the arc would be at a shallower depth than it is at present. So this region is weird. It's excluded. And yes, the reason is that there's some sort of decoupling mechanism between the slab and this overriding plate, but we don't know exactly what it is. is not underthrusting because that ends at about 40 kilometers. There's some episodic tremor and slip, but that's generally at much shallower depth, at about 50 kilometers depth. And there's no known deformation that occurs here. We have exhumed terrains that demonstrate this interface. It suggests that there's a relatively narrow shear zone, that you have shear deformation rather than seismic deformation along that. But why it ends at 80 kilometers, we just do not know.
So the question is essentially why it ends at the same place, or roughly the same place at all subduction
Yes.
zones. Yeah, not why the wedge is cold.
Right. So the 80 kilometers is plus or minus something. It's not a precise number, but it bears out in many places.
Do we understand why the shallower slab also have a lower Q? Where you actually have earthquakes?
I don't know. I always thought that this might be fluids that get dehydrated when they're further down. But Jeff, you are in the audience. You can answer this question. It's your diagram.
Yeah, I mean, everyone asks that when this figure goes up. So if you're going to show this, you should be prepared to answer it.
That's why we invited you to be part of this meeting.
So, I mean, a couple of things. The absolute numbers are much less if you can decode this weird color scale. There's about a factor of 5 less attenuation. The sampling, if you sort of look at where seismic rays goes, they kind of go like those lines that show that sample the upper stuff. It's really easy to image between the earthquakes and the seismometers. It's really hard to image under seismometers, so we haven't worried about it very much. But if you want to worry about it, you could make something up involving fluids, as Peter said.
I just did. This has been known for a long time, by the way. The people saw these waveforms when you just walk from in Japan, when you walk from the coastline towards the arc, and you just look at the same earthquake. It's very attenuated. When you get to the arc, it's not attenuated. And this is from Selvin Sachs, seismologist at Carnegie. We basically made an interpretation, essentially just on waveforms, back in 1984. A slightly more quantitative way of looking at this. These big circles essentially indicate high attenuation or low Q. The little circles indicate, this indicates high Q, this indicates low Q, where the volcanic front, the VF up here, seems to be the delimiter between the two. So this cold corner seems to, or this region that is high Q seems to be everywhere. We tend to call it the cold corner because it's also a place where we see some of the lowest heat flows on the planet. Even in a warm subduction zone like Cascadia, Cascadia is generally considered a warm subduction zone because you have young oceanic crust subducting slowly, and that creates for relatively high temperatures at shallow depth compared to, for example, Tonga or Tohoku, where you have old ocean and cold oceanic lithosphere subducting relatively quickly. In this place, we have heat flow that's measured from a variety of probes, as well as a layer that's imaged in seismology that corresponds to methane dehydration wells. And then, as soon as we get to the arc, we have large scatter. But before that, the heat flows are on the order of 30 milliwatts per square meter. And that corresponds to an average heat flow out of the Earth of about 100 milliwatts per square meter. 30 milliwatts per square meter is incredibly low. And that very strongly suggests that below this region, we have very low temperatures. And most thermal models, and we'll talk a little bit more about that on Thursday, in order to create these very low heat flows, you need to have relatively cold conditions. And this is where, this is from Heidman and Peacock paper, they really like this idea of a serpentinized or hydrated mantle. But it's seen in Q, it's seen in heat flow. Here's a heat flow database from the Japanese Geological Survey. The blue dots indicate low heat flow. The red dots indicate high heat flow. And pretty much everywhere right along the arc, you start seeing these high heat flows, which low heat flows in the Fore-arc. There's an intriguing incursion here where it looks like there's low heat flow going into it. So it's not perfect everywhere. There's some variations, but heat flow strongly suggest we have a cold corner of high Q material. Gets even better if we start looking at some high-resolution seismic studies that make use of converted phases that come up below a seismic array. This work by Michael Bostock using an array that was put over Oregon, very dense seismic instrumentation. And this is not a tomographic image. What these color changes indicate are changes in velocity that are seen by the seismic waves that come up to the array. Maybe the easiest place to start is the MOHO, where we go from red to blue, which is indication that we go from relatively low velocity to relatively high velocity. We go from blue to red to blue, where it's indicated that we have relatively low velocity here. And this is the hydrated basaltic crust that's subducting below Cascadia. When we get to a depth of about 40 kilometers or so, we start losing this low velocity region. And it looks like this is still a little bit, but it's not that much different. And this is interpreted, as shown in the figure, as ecliptization, where the eclogite has a lower seismic impedance contrast with the peridotite compared to the basalt. So what this is suggested that we look at active dehydration. We go from hydrated basalt to dry eclogite, and these fluids are probably bumped into this region. That stands out now for different reasons, because the continental MOHO, as you get closer and closer to this region, the arc is roughly here. It stops being dramatic, it becomes opaque. This suggests that the velocity here and here is roughly the same, and then it might even invert closer to... This is very intriguing. This is something that is hard to explain, except assuming that this region has much lower seismic velocities than the Mantle wedge itself. And these seismic velocities could be continental crust that is being dragged down there. That's not impossible, but typically we like to infer this as active serpentinization of the peridotite, where the fluids that are being driven off cause serpentinization that has a very strong influence on the reduction of P and S wave velocities, and therefore causes this disappearance of and potentially inversion of the MOHO there too. Intriguingly enough, Cascadia is the only place where this is shown with this much dramatic effort. A lot of other regions do not show this strong serpentinization at all. But in Cascadia, where we have a hot slab, so very efficient hydration, that's likely the typical place where we expect a lot of, maybe 100% serpentinization. So here's a quick diagram. I don't know, random, just to add a random thing in there, if you care about microbes and how life started, there's a great paper by Oliver Plumper that takes serpentinite mud that comes out of the Marianas Trench and talks about how these are the great places to start life. So we can take serpentinite and make life out of that. Serpentinization is relatively, may have forgot this from MGs and FEs, but Sarah and Christy will be able to correct me on this one. But if you take olivine, you add water, you create serpentinite and magnetite. Where serpentinite is a bit of a soapy texture. Are we going to see serpentinites tomorrow?
Yeah, we have some.
Yeah, good. The magnetite is interesting because that suggests that there should also be a magnetic effect that you can measure in that. And that has been not as successful, I think, as was hoped for.
Just so you know, Peter, 15 minutes until including questions.
Okay. Well, what I'm going to do is then finish up with the intermediate. I started at 9:30, so don't we have 90 minutes?
Yeah, we can run into coffee break, but it's supposed to be over at 10:30.
Oh, you're just giving me 60 minutes. Ah, I see.
Yeah, the introduction's quite a while.
So I am the victim. I am the victim of the introductions. Well, thank you guys.
Why don't you go an extra 10 minutes, please?
I think we need our coffee. So what I'm going to do is look at intermediate slab processes and maybe finish up quickly after that. So this is another receiver function analysis where we have the transition from blue to red to blue, indicating there's a low velocity layer here. This is now below the array in Alaska. What we see very nicely in here is the MOHO. It's a very strong velocity contrast. And we know that there's about 14 kilometers of oceanic crust going there. It's a Yakutak terrain that's essentially a doubled oceanic crust. And so we can infer the top of the slab from that as well by just extrapolating the MOHO by 14 kilometers. The black dots indicate earthquakes that are located within this velocity model. And they do something intriguing. This is below 40 kilometers. So this is intermediate depth seismicity that requires a special explanation beyond just brittle faulting. And they sit in the top of the crust at shallow depth, and then they intriguingly seem to dip into the slab, and then there's no more seismicity deeper down, about 120 kilometers or so. It's also the place where this low velocity anomaly becomes weaker and disappears. So there's a strong suggestion that somewhere between here and there is this hydrated basalt to eclogite transition with production of fluids at a depth of about 120 kilometers or so. This line that is in there is not drawn through the earthquakes. Well, it is, but that's to show a correlation rather than my sketching ability. This is the place where we predict from our thermal models, I'll talk a little bit more about that on Thursday, where this blue schist to eclogite, so blue schist is a high pressure, low temperature, mafic phases, where this transition occurs. And it lines up quite beautifully with the earthquakes. And so if you want to think about intermediate depth seismicity, I'm not going to talk about all of the mechanisms that have been proposed, but often fluids are being used, where the production of fluids can change the local volume and therefore change the behavior of the rock that allows for earthquakes. Before I give Sean, if somebody can give Sean the microphone and then take the question after that. One thing that's intriguing is that the earthquakes here are limited to the oceanic crust. They don't occur in the mantle. And that suggests a petrological control about where earthquakes occur. So, Sean?
Peter, I just have a question about the vertical uncertainty or the location uncertainty here. Because you see the blue schist transition is a kind of very precise location according to like thermodynamic prediction. But for earthquake locations, probably the uncertainty is like larger than that, right?
Yeah, so Jeff, what was the formal, it's in the appendix of this paper, by the way, so you can look it up if you're really interested. What were the formal errors on this? A couple of kilometers?
Yeah, I mean, they worked hard to do relative, getting technical, but in this paper we were very concerned about this issue. We had this very dense array of about 40 seismometers right on top of this small chunk of a subduction zone. We're trying to get accurate relative locations between the surfaces imaged with the scattered wave inversion and the earthquakes. And so there's a lot of sort of tests and you can imagine doing and coordinating the velocity models and making sure that everything's located in the same way. So it's within a couple of kilometers, the relative location between where the boundaries are and the earthquakes. And these are the boundaries, of course, that you use to define the boundaries in the thermal geodynamic models. So hopefully all of these errors are kind of systematic. So it's actually so given, yeah, I think how accurate these thermal models are, it's probably pretty good.
The formal accuracy of the thermal models based on just the discretization error that is being occurred is very small. On the order of a degree.
I actually believe the precision of the thermal models. But,
oh, no, don't do that. Don't do that.
What I mean is here, yes, we do see like dipping towards the greater depth, but if the uncertainty of those deeper, slightly deeper earthquakes is actually a little bit shallower, then we don't really see that dipping feature anymore, right? So I don't know.
It looks like the earthquakes are deepening.
Yeah, I'm just wondering.
Even if you move them up and down by a kilometer or two. So.
I mean, I guess could you get were you able to
microphone, Doug.
of the earthquake relative to the conversion?
Doug, can you please?
Yeah. Yeah. So,
Hey,
Sean,
breakdown of order here. Microphones.
Yeah. So Sean, they could look at the relative location of the earthquake relative to the conversion. It's not just purely the earthquake uncertainty.
Right, because remember, most of the earthquake uncertainties typically are due to uncertainties in the velocity models that you locate them in, but so are the depths to the conversions because the ray paths are actually fairly similar.
So isn't there an equal amount of uncertainty in terms of where you draw your line? Even though your thermal model is precise, this reaction doesn't happen instantaneously, right? So the same kind of controversy could be had about your line.
Well, I'm not sure it's a controversy necessarily,
about
but it's
real error,
oh,
real error in the data, right?
You should not believe that. That was what I was trying to tell Sean. You should not believe that line. But there's an intriguing correlation between the two. I hope you will admit.
Can I ask a question about the line? How does the slab top line get drawn? Because actually those dots don't look like they're that deeper relative to where the red-blue transition is, but they're different relative to that line. So I don't know how that slab top line is drawn.
Well, everything is based on this moho, which we think is relatively robust down to here, and then we extrapolate it further down. And then the top of the slab is just adding 14 kilometers, so shifting this by 14 kilometers.
So it's assuming the slab is constant thickness.
Oh, the oceanic crust is constant, yes. Which is an uncertainty in there too. So if the Yakutuk terrain has been going down for a while, so it probably is all the way down there. But if for some reason the crust thins here, that might be another explanation for it. Although the velocities kind of clearly continue, they're very thick. But yeah, let me move to a place where everything is more certain. Shall we do that? Shall we do that? Are you? But to help Sarah feel a little bit better about blue schist boundaries, so you're going to see these type of rocks tomorrow, I think. So everything is better in Japan. In Japan, they have thousands of earthquakes. They have thousands of seismometers. They have thousands of seismologists. Great place to work. This is seismic data from Saiko Kita's PhD thesis working with Hasegawa and Nakajima at Tohoku University. There's a cross-section below Sendai where Tohoku University is. The formal error on these earthquakes is roughly 1 kilometer or less with respect to the top of the slab, which in this case is determined from topside reflections. So while in absolute space, the top of the slab may move up a little bit, the earthquakes will move with it. So the relative location with respect to the structure is very, very precise. This is a region where we have the famous double seismic zone. Americans sometimes call this the double Benioff zone, which you really should not do. Benioff got into deep earthquakes in the 50s, whereas Wadachie already was doing that in the 30s. So it's a nomenclature that got into the literature, and please strike that. And certainly if you go to Japan, don't mention Benioff. You mention Wadachie, and everybody will be happy. But, I don't know why this is here, so let's ignore that. This one is intriguing again, because the top of the slab, down to about 7 kilometers, is roughly confining all of the earthquakes, again suggesting a strong petrological control on where the earthquakes are. The rocks determine where the earthquakes are. They don't occur in the peridotite as much. There's a few, little bit, and further down there's something is happening here. But most of the earthquakes are within the oceanic crust, which here is relatively normal, 7 kilometers. What is intriguing about the seismicity is that as you get below 80 kilometers depth right here, which is where we expect the coupling to happen between, so cold corner here, coupling starts happening, and then this earthquake seismicity, the seismicity steps down into the crust and then disappears from the crust. And in this particular case, again, there's formal errors on the thermal model as well, but since the convergence is so rapid and it's such an old oceanic lithosphere, the errors are smaller than they are in Alaska for the thermal model. And our prediction for where blue schist disappears and becomes eclogite happens to be essentially right on top of where the seismicity disappeared. Strong suggestion that blue schist has the earthquakes in them and eclogite does not. And maybe this is just fluids. So here's my cartoon interpretation. This essentially goes all the way back to Rayleigh and Patterson, 1965. I mean, we're continuously reinventing the wheel here, but my suggestion is that this blue schist out creates fluids, which go up to the arc. That makes the geochemist happy because they need fluids up in the arc. But some of these fluids also travel back up the slab, causing local weakening, and therefore the seismicity with that. It's a cartoon we have, and if you're interested to talk to Cian Wilson, we have some models that actually demonstrate that this should occur if we have hydrous flow in a subducting slab. But we even have very, very nice seismic evidence for the presence of free fluids at those depths. This is work by Shina and another student from Nakajima and Sendai, where they looked at earthquakes that are in the crust, and they looked at the difference between the P wave and the S wave, which take the same path up to the receiver here, and then waves that get converted from a P wave in the crust to an S wave going up towards the station. What this allows you to do, if you have enough earthquakes and you have enough seismometers, so the P wave, the S wave, the PS comes in between because it travels fast through the crust and then as an S wave up. This allows you to map out the P wave velocity of the crust itself, assuming you have enough earthquakes. So here's what they did, again, a cross section below Sendai, where we have the volcanic front. Here's a depth of about 70 kilometers, so this is roughly where we expect the coupling point to be. The blue schist out boundary would be predicted to be here. Within this region, down to about 80 kilometers depth, we have P wave velocities that go down to below 6.5 kilometers per second. We do not know of any rock that can have these low P wave velocities. Blue schist is higher, everything else is higher. This seems to be a very strong indication of the presence of free fluids that strongly reduce the P wave velocity. This is a map view of this, essentially looking down on the crustal velocities. So you're looking just at the crust that's then rotated up to the surface, where we see that there's a pretty strong bend. There's some excursions, maybe even intriguingly towards the volcanoes, I don't know. But if we look at the correlation between this P wave that is modeled in the crust below Tohoku and where the earthquakes are, we again see a very intriguing correlation. So these are the earthquakes in the slab. Let me do this once or twice. Where there's this band of earthquakes that beautifully aligns with where the low P wave velocities are, to me strongly indicating that free fluids are causing intermediate depth seismicity. So in the interest of time, I will skip the mantle wedge and volcanic
Peter?
arc section.
Peter?
So I think we should just move to questions. Yeah.
Peter, I had a question.
Oh, sorry, no, sorry. Yeah.
So if you go back to the slide before, so if you add on to that what you would believe to be serpentinization in the upper mantle, what would you expect to see in this image? And are you seeing it, or?
This method only maps out the crustal velocities. So this is uniform because there's no sensitivity. So we don't know anything about the velocities here from this particular method. If we look at tomographic sections that do P wave and S wave velocities in this region, the velocities are pretty close to normal peridotite, indicating relatively small amounts of serpentinization. Jeff wrote a Nature Geoscience paper on that earlier this year. It seems that massive serpentinization only occurs in the warmer subduction zones and not in cold ones like this, presumably because the fluids are not being produced till deeper down. So we have, I'm interested in coffee, you guys are interested in coffee, so are we right at the coffee break, Christy?
Right, you can go for another, say, 10 minutes.
I will, the rest of the mantle wedge, there's too much stuff in there to do that in 10 minutes. I don't want to hurry this. It was also something that, to give you the very brief summary, it's really hard to image the mantle wedge with seismological or electromagnetic methods. We're getting better. There's some intriguing correlations, particularly below Cascadia, where we have a lot of instrumentation, of course, in Japan. But it's really hard to directly map out fluid pathways. And so the geochemistry tends to be better at that than the geophysics. Very intriguing combination of geophysical techniques is going on in the study of arc volcanoes, where we combine GPS, INSAR, seismology, earthquake locations. We can map out magma chambers that don't look exactly the way I showed them in the Geology 101 slide. We can see them, we can correlate these things. And this is a burgeoning field that I think is very exciting. And if you are interested in this few slides I put together on that, I'd be happy to show them to you after this talk. Questions, Doug, microphone. Microphone. He's an organizer, can you tell?
Maybe just to provoke something, but one of the, and to raise an issue for the students of something that I think is not very well settled. There's this beautiful images of the double seismic zone there. What causes the lower zone?
I gave you my answer. I don't know.
Right. I mean, you may want to comment on the theories, or you know.
The earthquakes occur in the where antigerite is stable. They tend to not occur where antigerite goes to either phase A at high pressures or just back to peridotite. So there could be a correlation between that and dehydration from antigrade dehydration. But why the earthquakes are this distributed in this particular temperature pressure range, this is really weird. There's not that many places where we have really accurate determination of the double seismic zone. Teleseismics do not tell us much about the clear separation. There have been some attempts in the literature to do so, but it's really, really hard. There's some local studies, and I think you will discuss Cian's work on this, where it's intriguing that it looks like the colder the subduction zone is, the deeper the double seismic zone goes. But again, the error bars on that are relatively large. People have suggested that these are breakdown of fluids, but it's weird because this is actually not where dehydration is predicted. This is where antigrade actually is stable. Maybe one of the best suggestions is that fluids are shooting up. There's one of the many subduction factory papers that Brett Hacker and Jeff Abers penned that suggests that in a cartoon. And Manuela Facenda has made some models to suggest that this might actually be happening. I think that is about the state of the art. It is, since it's so diffuse and broad and not quite global, but almost global, it's a really weird region of seismicity.
It's in the mantle lithosphere portion of the slab often, especially in the cases where it gets deeper and deeper. So important thing to think about is like, what is the phase relationships in the mantle lithosphere portion of the slab? And there's other important hydrous minerals besides serpentine. And so there could be there's some loose, like depending on the thermal structure, depending on what you think the thermal structure is right there, there could be some other dehydration reactions.
How do
you get water there?
The outer rise faulting is a good way to introduce it, as well as hydrothermal circulation.
Yeah, the outer rise faulting doesn't go down to 40 kilometers.
Well,
so
we have some evidence that there's places where we see things that come from that deep that have hydrous minerals in it. So the question is, if we have some observations is there, even if we don't know how it gets there. Yeah.
Well, this is where Facenda's solution was somewhat originally. He said, well, in these cold subduction zones, you bring lots of water down, that dehydrates, and then shoots back up the slab. Since in between here and there, you essentially have the elastic neutral plane. It's really hard to bring faults down past that neutral plane. And that's why the outer rise hydration is very unlikely, unless we get direct evidence of faults actually going down. But they did. The seismic evidence for Nicaragua as well as for Alaska suggests they sold. Oh, I'm so sorry. Why did you not have a microphone? You're one of the organizers.
Well, he took it away.
Okay, the question, the question, audience, if you're still awake, the question from Christy was, well, there could be other hydrous phases, and there's some evidence for that coming up.
How deep could we know the outer rise faulting, or how deep could it go?
And the question from Christy is, how deep can the outer rise faulting go? All of the seismic refraction evidence that we've seen is that it sols out at relatively shallow depths in the mantle. And you don't have a microphone. You guys are impossible!
But Doug is going to show some evidence that it might go much deeper.
Jeff,
could
please.
you move forward one slide? I think this is a good one to ask. So you showed, or you suggested, that these free fluids are important, or essentially what allows those earthquakes to occur, the intermediate depth earthquakes to occur. Do you think there's an earthquake cycle for those intermediate depth earthquakes? That is there something happening in between earthquakes in a given spot, or do the earthquake only happen once in any given part of the volume? So is there some like earthquake cycle associated with those intermediate depth earthquakes as there is for crustal earthquake?
Great question. The answer is that I've not seen any type of periodicity, but then again, I don't do data, so maybe somebody who actually knows data and statistical analysis can see things better out of this. There's some very vague hints, unpublished PhD work by a student in Norway, that in the Hellenic arc, there might be some subtle signature of episodicity in these earthquakes that happen in kind of a similar region. It's very, very dicey, but it will be a great thing to try to figure out. If these are fluids, you somehow would expect that you might see migrating fluids over geologic timescales, and will be interesting to see if the earthquakes support that idea.
May I?
Is there some reason to believe the fluids would flow up slab versus just migrating upward? Is there a physical boundary to inhibit fluid flow?
It's the fluids will likely do both. There's probably a partitioning between fluids going out and fluids back up. The physical reason for why the fluids actually like to go back up the slab is that as you create the fluids themselves, you change the porosity and you get gradients in the compaction of this material. And this compaction pressure drives the fluids back up. And so Cian Wilson wrote a nice paper on this in 2014 demonstrating that the fluids are actually, it's almost harder to get them out of the slab than that they go back up the slab. So from a hydrological perspective, at these depths, we would expect the fluids to go back up.
So I have a quick comment. If I understand right, the dots here are hypocenters of earthquake. That's where earthquakes start. We do know there are large earthquakes at these depths, which will rupture tens of kilometers. So it will certainly rupture outside this zone over here.
Yeah, the magnitudes are up here, so the maximum magnitude is 5. So you would expect them to be over.
That's right, but we do have, say, close to magnitude 7.5 or 8 earthquakes.
Yeah, they're not plotted here. They limited it to magnitude 5.
Yeah, I mean that they can rupture into the zones without dots.
Yeah.
May I redirect your attention to this side of the room?
I'm happy to, sir.
First, it's just a quick comment that this, it's actually fairly common to have really large normal faulting earthquakes seaward of the trench. And it's been proposed very early on that some of them may rupture to a depth of, say, 60 kilometers or so. So it's not just reflection imaging that we can use to trace the depths of the normal faults. And the question is, back to this cold corner or whatever you want to call it. Now, in South America, as we know, there are many places where the slab remains essentially flat and there is no active volcanism, but eventually the slab would have to bend and go down. Do we know very much about that area? Does those regions have cold corner or high
Yeah, the sort of flat slab below Peru, flat slab below Mexico. I don't think there's any strong evidence in those regions for a cold corner. In Mexico, for certain, the Moho continues straight to where the slab subducts. And so there's the suggestion there's not massive serpentinization in that region. So there will be variability. It is just that where we have looked with high enough precision seismic or heat flow tools, we've seen this cold corner. We've not seen it everywhere, but I think that is because of lack of adequate sampling. So, thank you. The room got dark and we might as well have been at Denver Airport or UC Berkeley for that matter. Those are Rocky Mountain ravens. There's actually a second one that's hiding right there. They love the garbage that's being put out by the folks at the Timberline Lodge. So let's start with some history. And I'm going to show some old people. And I would like to ask you, well, at least it keeps us entertained, right? I'd like to ask you if you know who this person is. This is a German scientist. He's a meteorologist and a polar explorer. Wegener, Alfred Wegener. He was a heavy smoker. He didn't live very long. In the 1930s, he died on Greenland as part of an expedition. Everything went wrong there. They had frostbite. He skied himself to death. He got a heart attack and was buried in Greenland. But of course, he was very important in providing the theory of continental drift, which now in retrospect was something that we all feel very comfortable with. The idea that we had Pangea, which is found by overlap in geological terrains, in overlap between fossil species that diverged as soon as the breakup occurred. And importantly, from Wegener's perspective, glacial features, including glacial striations, that strongly suggested that a number of these continents were on the South Pole, whereas aside from Antarctica, most of them are not. Unfortunately, this ran into a little bit of trouble. Particularly the seismologists were not the friend of continental drift. Seismologists had a good argument, I will admit. They said, well, S-waves penetrate through the Earth's mantle, therefore it's a solid, therefore it cannot move. And unless you had entertained yourself about Maxwell time and the idea that rocks can flow over long time scales. This was a strong argument. And Wegener was pretty philosophical. A year before he died, he wrote kind of the idea, in a way I like it, I also find it very tragic. The final resolution can So it's a pleasure for me to start the lecture program of CIDR. I ran into a little bit of a cold, or a cold ran into me, I guess is the physical term, so I hope I'll get through this without croaking too much. But one way that I discovered that if you have a cold in your lecture, that the role really needs to switch from lecturing to audience participation. And so I'll try to engage you as much as possible, at least in the beginning, for that. What I'm going to do is to provide you with a very broad overview of how we use geophysics to study subduction zones. This, of course, is an impossible topic because there's an enormous amount of geophysics and enormous amounts of subduction zones. And so all I'm going to do is to really provide a few highlights of how we study things and talk a little bit about how we understand the usage of geophysics. This is primarily intended for the non-geophysicist in the room, or the seismology for the non-seismologist and the geodynamics for the non-geodynamicist, etc. I think that is the best approach to CIDR that I've seen work. So if you get a little bored when I explain receiver functions, it's okay. You won't be bored when Christy talks about the geochemistry of subduction zone this afternoon. So a quick overview. I'm actually going to start with mantle convection and try to demonstrate to you that a long time ago we already knew a lot about what we now know as plate tectonics, even though it was not named plate tectonics at the time. And I'm going to give some geophysical applications of studies of how we look at the incoming plate, what's happening as the plate is subducting, the deep processes, where deep in my terminology here is relatively shallow for the deep earth scientist, and then we'll move back up through the mantle wedge and the overriding plate. A lot of this work has been, a lot of work that I present is based on work that's sponsored by both Margins and Geoprisms, which is about 2 decadal probe, and was therefore able to do the first marine gravity measurements. Anybody? Yeah, Weening-Meijners, excellent. Felix Weening-Meijners, he's one of the people that actually, oh, I forgot to mention, Arthur Holmes also died on his skis. He had a heart attack while recreational skiing, so Weening-Meijners died in his sleep, I think, in 1966. His major contribution was the development of new gravimeters, and very spectacularly, and if you have never seen this, this is worth looking up, gravity maps over the Indonesian, what we now call the Indonesian Trench or the Indonesian Arc, with very large negative gravity anomalies, with slight positive anomalies outward. And this is what we now would recognize as just the trench and the Fore-arc bulge. At that time, we didn't have good observations of the seafloor. It was too deep for most submarines, and the gravity provided that first idea. So what this led to was the idea that we have missing mass. And that's really weird, because if you're missing mass, of course, the stuff will fall in and will fill that in. So if you have this missing mass, it must be dynamically supported. And this really was the first confirmation of the Holmes convection idea of the support continental drift. This is all in the 1930s. An American who kind of tied everything together. There's a high pressure apparatus named after him still. He was the first person to deform, or not the first, but one of the first people to successfully deform rocks and demonstrate that mantle silicates actually deform as a fluid over geologic timescales. His first name is David, and the second name is, you can't participate. The second, well, yeah, of course you can. Second name is Griggs. He wrote a very nice article that's still incredibly readable in 1939. And his major contribution was to add this idea of fluid dynamics to mantle convection, strongly supporting the Wegener support for, or the Weening-Meijners support for the Holmesen idea for Wegener programs to study the subduction zones and continental margins, including rifted margins, from a terrestrial and oceanographic perspective. And so this is one of the few programs that get support from both OCE and EAR in the National Science Foundation. So to start off, is it possible to reduce the light a little bit, or Okay, so in order to start, and I really would like you to feel very comfortable asking questions, and maybe in particular the students and the postdocs before the senior participants. So feel free to interrupt me anytime when something's not clear or you have a question. And to start off this process, I just want to get to a few questions from you. I mean, what mountain are we looking at here? This should be straightforward. This is Mount St. Helens, lateral blast, 37 years and a month ago. It exploded sideways, killing a few people who were in the wrong side of the volcano. We had a meeting in 2009 where we took a field trip with a number of the international participants, and we all took pictures of this hazy mountain, and Ikukovada was the only one that was smart enough to put a few of these tree stumps in front of it, making for a much nicer framed picture. Okay, second one, Adam cannot guess, and Sarah cannot guess either. This one might be a little harder. Which mountains are we looking at here? This mountain looks a little bit like Mount Crumpet, the Grinch. Any guesses? It's also in the Cascades? No, it's not. Can you speak up? Because It is Jefferson, yes. This is Mount Jefferson, and behind it, very vaguely, you can see the Three Sisters. This picture was taken during the 2009 meeting that we had on Mount Hood. They have a very nice timberline lodge there, and this was the view we had at breakfast. So fantastic, so everybody was taking pictures. And then as the meeting started, this enormous PowerPoint screen came down, and only come from geophysics, because it's the only science that is precise enough. Were geophysics come to the conclusion that I was wrong, I will gracefully admit defeat. So the geophysicists were the problem makers, and he thought that they were right at the solution. In a way, some of the geophysicists provided support for his idea. So here's this gentleman, two pictures, one just before he died in the 1960s, University of Edinburgh. He's a British fellow of the Royal Society. He was a geochronologist. He was interested in radioactive decay. And he supported Wegener's idea that continental drift was supported by mantle convection. His first name is Arthur, and his second name is Holmes. Okay, Arthur Holmes. He provided the idea, since he was interested in radioactive decay, and he was one of the first early people who tried to make estimates of the age of metamorphic terrains. He estimated some terrains to be 1,600 million years, which at that time was much longer than what people really like to think about as the age of the Earth. But he also knew that radioactive decay could create heat, and that could therefore fuel mantle convection. And so his idea from the 1930s is really not that much different of what we see in textbooks. This is just an idea, there's no direct support for it, but the support was provided in large part by this gentleman, who was an early marine scientist. He measured gravity by a very long distance. He is my academic grandfather. You know his name, Ingrid? You were at Utrecht, his famous date in the 65. He was a very tall man, a little taller than I am. You can see him up here standing amidst people that were on the Onderzeeboot, or the submarine. I don't know whether he was wearing that tropical helmet because he was in Indonesia, or that he needed something to protect his head as he was aboard that very small submarine. But what he did was to develop gravity measurements and use the submarine to get below the waves